I think I could not have exaggerated any better than you. And it's really a great pleasure to come back here. The last time I was in this exact spot was my thesis defense, which I realized the other day when looking for some slides that it was August 10, 2005. So it's been a little while. And it's nice to be back. And I also managed to find, unfortunately, a couple of old pictures, but here's a picture from when I was in grad school. And I think you should be able to recognize some of the people here. I mean, that was me. That's 2001 in Calgary in Canada, about to go to the Engineering Foundation conference in Banff. And there's Basan. And then I guess Bruce would recognize everybody else. I'm not sure if anybody else would know. Yeah, Frederic and Dorota and Kausto Brown, Junior, and Arnold Guerra. And then unfortunately, I thought I had a picture from that trip with Bruce, but all I could find is a picture that includes Bruce at Lake Louise in 2001 too. I was the one taking the picture, so there's Basan again. I don't know if you have that one, I should send it to you. So, that being said, I apologize for the slightly generic title, and the problem is that I pretty much am interested in anything that has to do with photons, electrons, and ideally some computation device nearby, so I've done a lot of things. So, there's two major parts of it. One part is about optical breast imaging, and the other is on neuromonitoring, also with diffuse light. When I moved to Mass General Hospital, that's the first thing I worked on. That's partly because I saw Bruce doing all this great work with the DOSI, and I thought, well, after I spent the entire time in the lab building a system and, eventually imaging egg, fertilized egg membranes, I thought, let me try to actually measure some people. And then along the way, I learned more and more about this diffuse fluorescence spectroscopy technique for measuring blood flow and the whole world of neuromonitoring, and I had the chance to slowly grow that side of my research as well. So, starting with breast cancer, I think if you're here, you would know a lot of what I'm about to say, but it is still a major health problem. It's the second most likely cancer for women, and there are, it's almost 1 in 8 women are likely to develop it. And the standard screening technique, which is mammography and now three-dimensional digital breast tomosynthesis, is doing a fairly good job of finding lesions, but there are some issues. And then primarily that dense breast tissue is challenging because the way mammography works, it is looking at essentially tissue X-ray absorption contrast. And water and tumors don't look that different really. So you're seeing the fibroglandular tissue like a tree, and then you're trying to find the oddly shaped nest in the tree. And it's really a lot of, actually, I'm pretty sure there's a tumor here, but I think it's this one, but it's the way radiologists do it is they look at strange shapes. And anything that has spikes coming out of it is definitely bad. Things with a smooth boundary are good, and then there's so much in between. And then, because of this, the typical way that a clinical breast clinic works is they are going to try very hard to not miss cancer, so they're going to biopsy everything that's suspicious beyond a certain level, and only one biopsy in 4 or 1 in 3 actually turns out positive, which is a good thing for the ones who get a negative biopsy, but they're spending time being worried, and there's also extra healthcare expense. So in other words, there is a specificity problem. Sensitivity is, at least the way that practice is being done, is pretty good, but specificity is low. So this is where optical imaging, and again, I have here one of the great pioneers of the field, can help add specificity especially. And at MGH, even before I came, there was this effort to combine optical imaging with mammography. This is a picture of the original system that was installed, I think, in 2005, and we have it running until 2010 or 11. This is a prototype GE tomosynthesis machine. So this is a typical mammography machine. For those who haven't seen one, this is the X-ray detector. It's under this carbon fiber cover. This head is where the X-ray tube is, and then there is a plastic plate here that compresses the breast. And tomosynthesis means that this head can move plus or minus some degrees, and it's like a partial angle CT scan. You get some resolution. So typical digital mammography these days may have, I don't know, 10 micropixels or so. There's a couple of megapixels basically, X, Y. Z, maybe get 5, 10 different planes, but that's much better than one. So it's essentially a forest of fibers delivering a combination of steady and frequency encoded light. We had this hybrid approach because it's more expensive and slower to take measurements in frequency domain. There's more information, which is why DOSI uses that. And I can go through the numbers, but essentially we ended up with about 30-something positions for each subsystem and then 30 detectors. And took imaging. At the time, we managed to make it as fast as 7 seconds because I'll show you later why we're trying to rush. And the breast stays in compression, so this plate here actually has source fibers. They come from the side and they shoot upwards. Then you can extract the metal, leave the cassette in place. Then this big box here contains fiber bundles that capture the light that goes through. They can also be released, and then you're just left to the breast in the same position, but now you can take the X-ray. And you have completely co-registered information. So to obtain optical image, you need to do a model-based reconstruction. So it's we had an implementation of the standard diffusion approximation as a finite element solver. I'm sure it's somewhere on the other slide, but Dr. Chen Fang, which came from Dartmouth and GH about the same time I did developed a code for microwave that actually did finite element, and then we started using it. We're still using it actually. It's termed redboard. And the mesh is derived from the volume from the X-ray, and then we co-register the allocation of the optical measurements, and then do a two-step reconstruction. First, find the average optical properties, and then let that be refined into a dynamic image. Because it's difficult to get from an initial gas dynamic far away to a full image in one step. So this is what image reconstructions look like. I guess that's one of the downsides of optical imaging. The resolution is a bit low. This is a fairly large tumor, and what we see is, like many other groups have seen, increased total hemoglobin concentration, not necessarily too much contrast in saturation, and also higher scattering. And I have to admit that there's always a good question whether there's crosstalk between absorption and scattering. So there is physiological reasons why they should be related. There may also be a crosstalk. The blood has more scattering than the normal tissue. So in this case, all of our imaging is a reference to the same breast normal tissue because there is no standard breast. There's so much variability between people that you cannot have any global standard. But also absolute imaging is tough. Calibration can really make the absolute values change, especially from person to person. So these are reported ratios here. So for total hemoglobin, the fibroglandular tissue is kind of outlined with this fine white line. It's 50% higher. The tumor here is about twice higher. This is the final reconstructed result. In the tissue, there's going to be higher contrast because we lose some of that to the diffuse propagation, and some contrast in scattering coefficient. And if we look at this was published by Dr. Fang in 2011 as the key finding is that sorry, I think I got lost on my own slide. So the total hemoglobin concentration is about, I'm very sorry, I don't know where this came from, but that actually, it's about 20% higher total hemoglobin concentration in the fibroglandular tissue versus the normal tissue, plus or minus 10%. The tumors were 37% higher total hemoglobin concentration, also plus or minus 10%. So that was a statistically significant difference. Oh, I'm sorry, these are just the p-values. I apologize. I should have had the actual table here. So the radiology paper in 2011 has that. So most of other groups have seen also a significantly higher amount of blood in the tumors. For CIS, we also saw that they have a lower saturation. It's a kind of artifactual because there's not have blood inside. This is underutilizing the X-ray. We are essentially only using the outer boundary, but you can use more of the information. So, for example, you can look at the gray values and do a segmentation, essentially a compositional segmentation, that if you know what intensity value is going to be adipose and what's going to be almost pure fibroglandular, you can decide that every voxel, what is the mix of the two. And that creates a spatial prior that essentially we then constrain the reconstruction such that the total hemoglobin concentration or the optical properties in each tissue type are fairly narrowly packed, It's not strict, so it's not so-called hard priority. In the optimization, the goal of any optimization is to reduce the residual of some kind of cost function. So the cost function, you can tune what you're sensitive to. So basically penalize variation in the optical properties of the same tissue type. And that way, the optical reconstruction is tuned towards the composition from the X-ray and then allowing for a tumor as well. So this joint reconstruction is going to look a bit more like the X-ray. But then when we have a tumor, this additional component shows up. So it much better localizes the actual contrast and substantially increases the contrast recovery. I think on a tissue level, you expect 3 to 4 times perhaps the vessel density in a tumor, so you'd expect hemoglobin concentration to also be more than 37% higher. So this is one way to improve optical reconstructions. And when this was revised, taking this method into account, the p-values were improved for differentiating malignant versus benign tissue. So I think I forgot to mention that that's one of the biggest challenges, telling malignant versus benign, because they are all masses. So that was a good result, but we also noticed along the way, and that's really what I came in primarily in the beginning, a variation in signal, as we mentioned. So I was saying, oh, it took 7 seconds. Actually, initially, we're taking 60 seconds to gather the data. And we noticed that, well, first of all, we had some issues with the quality of the images, and then also noticed the signal is not quite steady at the time. The system was a hybrid that had part of it using a time multiplex light delivery to sample multiple locations, and a few locations were monitored continuously. So those signals are plotted here, and then we see up to 10% signal change. So signal going down, that probably means absorption going up, could be scattering to button. So we wanted to see what this is about. So that was my first project as I started in that channel, to build a system to measure the breast properties dynamically as you apply compression. So this is the second iteration of it, where it became an imaging system. Essentially a similar geometry to mammography, a compression system. This one has a computer control to actually apply steady pressure. This system here is what's called a TECAN CW6. It's 32 laser sources and 32 detectors. Each source has its own kilohertz level modulation frequency. So then by taking a discrete Fourier transform on every frequency, you can measure simultaneously all the sources on every detector. So this was initially designed for brain imaging, and it can go 25 hertz with 1,000 channels. It's a bit overkill for breast imaging, so it downsampled to 1 hertz. And between these two boxes, I had 6 wavelengths and 64 sources and 32 detectors. And then there was a small frequency domain component. This is an ISS Imagent device that had one source location and 4 detectors to give us some measure of absolute properties, because with a continuous wave system, we don't get absolute properties. So the bottom is where the source fibers go. This is this diagram. Then the top is fiber bundles that go back for the CW detection. And this striped object is a iScan pressure map. We wanted to see both the breast boundary and also the amount of pressure applied. So these are literally conductive ink stripes. That wherever they cross at 90 degrees, they make a sensor. The farther you push, the less resistance they have. So they can image live the amount of pressure. The CW imaging was in transmission, so that's a tomography source, and the frequency domain was just kind of local. In the end, we really primarily analyzed the CW transmission images. And this is the schematic of what we did. It was a bit of a torture-like protocol, that the translation stage would move down to compress the breast, try to quickly apply about 6 to 8 pounds of pressure. With continuous monitoring, we run the frequency domain measurement to get absolute properties during that compression. As soon as things are steady, we turn on the CW system and get tomographic imaging at high rate, hold on for 22 minutes, and repeat this 3 times, which I agree repeatability. And just said all that. This is what kind of things we saw. So this is an example of a patient that had cancer here. And we looked at both total hemoglobin concentration and changes during the compression. So just going back here, what we did was essentially image starting at this point. So we looked at differential imaging as the breast stayed compressed. And we looked at the tumor region of interest and the rest of the breast. define the tumor based on the MRI or other clinical imaging, which is a little bit sketchy because it was not perfectly co-registered. So we're using optical contrast to find our region of interest. So that's why later we moved on to a different approach that's a bit less open to potential bias. But this is the interesting part, that as you hold the breast in place, the force actually starts decreasing because the tissue expands. So it's not like the machine is actually applying constant pressure and continuously adjusting. You just compress and hold. So it's like a slow release. You know, the force went down 30% or so. So what happens when you do that? The blood starts to come back into tissue. But it comes differentially between the tumor region and the normal tissue. So the normal tissue starts, it's not that much of a change, but it starts to go up fairly quickly. Tumor goes down for a while and then continues to go up. So again, this is as you hold the compression. And saturation also has a different time course. So saturation, I'm assuming you guys are familiar with oxyhemoglobin divided by total. And when we conducted actually a therapy monitoring study with funding from the Common Foundation, it was 2009 to 13, just looking at the baseline data first. We had 17 analyzable patients, and these plots show the total hemoglobin, oxyhemoglobin, deoxy, and saturation changes during the compression. That's why they all start with 0. And historically, I should have changed this, but my postdoc at the time decided to use blue for cancer. So blue is actually the bad one. So you can see how the normal tissue starts recovering almost immediately as the pressure decreases, and the tumor just has a delayed response. It definitely goes down a bit in the beginning, and then it recovers sooner or later. It seems to be mostly driven by oxyhemoglobin, which probably means it's driven by new blood inflow. Deoxy starts going up because you're reducing blood flow, and therefore you're starving the tissue a bit, so it has to consume more of the oxygen and produces more deoxyhemoglobin. And then, yeah, saturation, it's also decreasing faster in the tumor. So there seems to be a statistically significant difference in the way that these two tissue types behave. And if we set a threshold for how much change we consider to be malignant, then this is the ROC curve for that. Now, I do admit this is malignant versus healthy, not malignant versus benign. So it's a much easier case. So just the amount of decrease of hemoglobin concentration actually can distinguish. And I'm not sure if everybody's familiar with this ROC curve. It's essentially on one axis is 1 minus specificity. So I'm afraid of giving a definition just in case I get it wrong, but essentially sensitivity is the cancers you're actually finding that were there, and specificity is, yeah, I probably should not give you the definition right now, but we want to have, yeah, we want to have both high sensitivity and specificity. So when you have a medical imaging system, this applies to any quantifiable medical diagnosis, you're going to have a curve like this, and you have to decide where are you going to operate on it. You can choose high sensitivity at the expense of specificity, or the other way around. So when people quote a single set of numbers, they just pick a point on that curve that they find best for some reason. What matters is this area under the curve. 0.5 is essentially chance. 1 is perfect. So, you know, mammography, I think, is around that for detecting cancer. So this is the first study that we did that looked at dynamic contrast and sees that the mechanical properties probably have a large role to play in here, and as well as the metabolic properties of the lesions, the malignant lesions. So we wanted to see if we can exploit this to predict neoadjuvant chemotherapy response. So again, this is the pioneer essentially of the studies, so I'm going to repeat a lot of what you've heard before, I'm sure. But the point of neoadjuvant chemotherapy is this chemotherapy given before surgery with the goal of shrinking the tumor, either so that it's possible to operate, or that you can do a breast conserving surgery. And usually it's done for patients that come with fairly large tumors from the beginning. I mean, they're not diagnosed until they have locally advanced breast cancer. So the issue with chemotherapy is that it's, even with improvement in genetic testing, is a bit of shot in the dark, especially for some subtypes of cancers. It's called triple negative. So there's some receptors that define the cancer subtypes. Some tumors have none of the classic receptors, and those are the biggest unknown right now because there is no targeted agents. So you have a course of treatment that takes months, and you may or may not have a good result. And the key question with neoadjuvant chemotherapy is, can you make the tumor disappear? Because statistically, it's the only outcome that's been shown to improve the disease-free survival and overall survival. So basically, how long you're going to be cancer-free or how long you're going to live literally after cancer treatment. Short of that, it's almost as if you don't have to do it. I mean, it's not so simple, but the goal is to find a complete response. So this study was fairly small, so we tried to enroll 30 patients, and in the end managed to obtain good data at enough time points over 13. So it's a bit worse than what came out of the acne study that Bruce ran, but it shows you the challenges of doing optical tomography and get good data from it. So in the end, we had 13 patients that came back for day 7 after baseline, and then also 7 that came back 30 days later. And we wanted to compare the changes between day 7 and baseline and day 30 and baseline to see if we can predict the outcome. And we had 6 responders and 7 non-responders. Because of the small size of the study, we just picked 50% decrease in tumor diameter as a response. We also look at data for complete response, and it's not very different. But this was published in 2017 in Biomedical Optics Express. These curves, day 0, are what you saw before. That cycle is just how many, we repeat the compression several times. We wanted to see if it's repeatable and also if we really have to do it multiple times. It actually seems the first cycle is doing fine. So in the beginning, you see a difference between responders, between tumor and normal tissue, and now the cancer is in red. Both in the responder group and the non-responder group. But then the non-responder group doesn't change that much. It actually seems to get even worse. The responder group, these differences disappear. Actually, they kind of disappear by day 7, but there's a statistically significant difference in the changes by day 30. So this just summarizes all the statistical comparisons we've done. And it's really, especially given with the multiple comparisons, these kind of p-values are the ones that matter. And looks like, we have to compress 2 or 3 times to get repeatable values, and at day 30 we can tell whether somebody's going to be a responder. Saturation had similar results. That also, it took a bit longer for them to overlap, but the responders essentially, the cancer started behaving like normal tissue. The non-responders didn't. And this is the statistics for it. So we try to do some kind of ROC curve, and it's a very small number of patients, so I would not really emphasize this too much, but it does seem to give more information than a coin toss. So this motivated us to go to a fancier X-ray mounted optical system. So now we wanted to be able to both get co-registered images with a independent reference for the tumor location and have high temporal resolution. That was the design goal of the system. So now this is the first FDA-approved tomosynthesis machine from Hologic, and the Mass General was one of the first sites to install that and switch to all tomosynthesis actually since 4 years ago. It's very similar to what I showed before from GE, and GE eventually got their approval too, even though they started first. Somehow they got scooped by Hologic, and that's the same idea. This head moved laterally. This goes down to compress. This is the X-ray detector. And we were very ambitious and actually coupled glass fibers to little plastic fibers so that we can take the X-rays through the plates. So this here is where the fibers spread out and go into, on the side, coupled to plastic fibers. And this was fun to machine. It took about 2 weeks on a milling machine. And then the little buttons where they're shaved at polished at an angle so that through the internal reflection, the light comes out upwards. And then on the detection side, the fiber bundles and with a little prism. So this is the system diagram essentially. Again, a collection of continuous wave and frequency domain components. Continuous wave can run, as I was saying, 25 Hertz. Frequency domain, this was a faster design. It's actually, we're quite proud of what happened here because the detection side is quite innovative. It's doing a complete complete digitization at full sampling of the signal. So this is 70 megahertz. The ADC runs at 118 megasamples per second. And there is no need for analog IQ, and the analog signal length, path length is a couple of centimeters, and there's very little chance for noise. So this comes very close to the pure detector performance. And this very smart guy called Bernard Zimmerman, he applied a partial processing algorithm inside an FPGA on each detector card to shave down most of the data. Essentially does a DFT, the discrete Fourier transform. Doesn't complete it, but does most of the work such that then a fairly small data rate stream can go into MATLAB to finish the work, and then we just get directly the reading of the power in that frequency band. And that way, we have very good noise performance, and also we can multiplex multiple sources. So right now we have 67.5 and 72 megahertz. The algorithm that works fast requires some integer ratios between them, but we could fit probably 4 frequencies at the same time. So before we had to have a switch to switch wavelengths. Now this can simultaneously measure multiple wavelengths at once. So this internally runs at 90 hertz, and essentially switching between locations will lose a sample or two. So depending on the duty cycle we want, we could actually even run the frequency domain at 5 hertz or more. We run it about 1 measurement every 2 or 3 seconds for SNR, but it's quite a flexible system. So we get an image about every 3 seconds. That's what the goal is. And then we put it in a much nicer enclosure so that it's actually sitting in the breast imaging clinic. And when a patient is scheduled, then I would train a radiology technician to mount this and take all the measurements. The frequency domain. Right now this is 67.5 and 72. One is 690, one is 830. So, yes. Anywhere from 3.5 to 9 centimeters. Well, so optical properties matter a lot. There's definitely a burst where we can get a signal that's definitely above the noise power like 11 centimeters, but that's not always the case. So we usually are able to get diagonal measurements at least several centimeters away from the direct transmission. Yeah, I mean, actually I'm not showing you too much, but the more you try to push it, the more other errors in the system like crosstalk or light leakage is going to mess up your signal, so you don't want to go too far. But there's definitely transmission. I think breast up to 6 centimeters or so, no problem doing measurements in transmission. It really depends how dense they are. For very adipose ones, you can have 7 centimeters and you get good signal up to like 10, and then that will give you some tomography. Well, I'm not claiming that we're going to get much Z resolution. Maybe we have like 3 independent slices, in Z from the tomography. So, but the more measurements, the better. It's already underdetermined. We have typical mesh has 7 to 10,000 nodes that we're actually trying to reconstruct the properties on. Measurements, a best case scenario, we have 4,000. Realistically, it's more like 1,000 to 1,500 that actually are working simultaneously. Yes, 3 millimeter size APDs, 80 megahertz bandwidth, 0.2 picowatts per square root, that's equivalent power. And then when I characterize the system, it comes to like 0.3 to 0.4 sometimes. That alludes to what I was asking at OSA, because you were there, that actually I tested the ISS metal system, which is also PMT based. The PMT should be a couple of orders of magnitude better. But in my testing, it was only slightly better than this. So, no, but it was a one-to-one comparison, same fiber going to both systems. So, no, this is to the fibers. No, they are not that small. I mean, we're using these modules from Hamamatsu, they're this size. And the detector cards are this size. So this each slot here is a detector card. And it's this long with all the circuitry. So that would be nice. And I know Dartmouth tried to use these large silicon photodiodes directly in contact. I thought I have not seen too much came out of that. I think it's a bandwidth issue with the large size. And yeah. So fibers are a mixed blessing. They're flexible, but they throw away a lot of signal. I think the throughput here is about 10% on each side. So it's not, yeah, that's trade-off in any design. So in any case, but however, I was just saying that I think the circuitry in that ISS system is not fully exploiting detectors. I think this is I'm happy that this design can come even close to it. There's an advantage to it. If it is 5 orders of magnitude and anything, you basically don't need to change the gain. You can just use one gain and be done. You have to tune the gain for the PMP system, and I think at best there's 3 orders of magnitude. So, in any case, it's nice to play with the hardware. It's also not bad to play with phantoms, where we had this again, this guy's very ingenious. found jeweler wax, which can be both melted and dissolved in water. So he cast these balls. I mean, as a group we worked on this. So we want the phantom with cavities that don't have glass walls. We tried to put glass spheres in, and the light piping completely messed up the contact. Essentially, it made it more transparent, even if you put ink in it. So we cast these wax balls here, pour silicone around them, and then pull this metal tube out, push hot water, dissolve them, and then we end up with a nice cavity. This is the X-ray of the cavity. And we have a very clean way of putting some, absorbing substance in there and then seeing if we get what we expect. So in this system, yes, it works pretty well. 3 different sizes. This is half an inch, 3/4, 1 inch, and this is dynamic changes of the signal. That's published in JBO last year. And this is what our artifacts look like on the X-ray. So there's definitely a projection. I mean, there's definitely shadow left above plastic fibers, but in the middle slice, it's not too bad. So this is from the research scan. This is from the clinical scan. They're not really that different. We had some other issues with the plastic fibers. They actually ended up aging and cracking, unfortunately, from the X-ray. So we have to iterate on the design. But it's in principle possible to do simultaneous imaging with optical. So the goal of that project actually was a grant was to build a prototype, and I think that's a recipe how one could build an optical and X-ray system. And the imaging, in this case, we position the patient, take acquisition. We tried a few protocols. I mean, essentially now we're basically doing the radiology technician would determine the amount of pressure that normal mammography positioning requires. They have the guidelines on how tight the skin should be, how the breast should be fitting in there. It's not about force. Force is whatever they end up with. So we asked her, put the person in as you expect them to, as you would normally do it in your job. Write down the force, let them go, put them back, kind of hold them on the position, and then start the optical system, apply half the pressure you just determined earlier. After a minute, push a pedal to stop the optical, compress fully, push the pedal again to restart optical, take another minute, do the same thing, and then go back to half compression. So we want to see these transitions as well, because the changes as you hold are actually quite small. So we're worried that maybe with this, maybe we don't see enough. So this is one of the protocols. We go from full compression to half compression, or the other way around. So some example images here. This is a benign lesion. We adjusted the color bar so it's transparent under a certain level. So it didn't stand out that much from, there's definitely some fibroglandular tissue here also showing up. But when we reduced compression, there wasn't much change in the benign lesion, but the rest of the tissue went upward. So that is actually different from what you see with the malignant cases. I have 2 to show in a moment. So here, the same thing we did. We went from full to half, and then we had increase in the tumor area more so than the tissue around it. Now, this unfortunately does have contrast here, but there's definitely some artifacts to the shape of the breast too. And I'll come back to that a bit later. And this is another case, but this is looking the other way around, because the next case we actually went from half compression to full compression. So here, tumor stood out pretty nicely in total hemoglobin contrast, and also stood out quite nicely that as we applied more force, is the tumor that changed the most. So half mammographic compression kind of put the normal tissue in a steady state, apparently. And it's dynamic, of course. So we don't see as much changes before. Maybe it has to do with the way the mammographic compression is done. And this is a work in progress though. So we continue acquiring cases. We want to see, our hypothesis at this point is that this kind of behavior where you go from half to full compression is going to distinguish malignant versus benign lesions. So to come back to that. Also, the amount of response to this, we hope to call it chemotherapy response. So that's what we are working on. And to understand this better, we also try to build a breast MRI elastography system. I mean, we didn't pioneer this, but we are in an MRI center, so we figure we try to do something with MRI. And we have, essentially, to do elastography, you need to have an actuator that sends vibration to the tissue. And then there's a sequence that's motion sensitized so that it's actually tuned so that the gradient switch such that it catches the tissue in one position versus another repeatedly until you accumulate the phase difference, and the phase difference tells you where the wave is traveling. So this is actually how you can see the wave. Literally, this is the phase of the image, and the longitudinal shear, sorry, the shear wave is traveling. Longitudinal wave goes way faster, so it disappears very quickly. So all of this is shear wave, and you can get the shear modulus. So you can reconstruct that. This is a phantom where we had some inclusions that had both optical and X-ray and mechanical contrast, and in the phantom we can see it. And we're at the stage where we're trying to get patients put in this. So that's kind of the breast summary. We have the system now that can do tomography with X-ray, and we really want to exploit it to find out the dynamic signatures and static ones, of course, of patients that go to chemotherapy. And I have a protocol opening up that's specifically look at HER2 positive and triple negative patients. And we spent a lot of time getting all of this, the process of getting images together. So tomography is quite challenging. If you can avoid it, try. This is a paper that we published recently about the impact of various kinds of errors on the tomographic images, like how much can you be off in X, Y, rotation, tilt, crosstalk, light piping. It's a bit scary actually. That, you know, you could be 2 or 3 millimeters, 2 millimeters off is too much. Tilt, you know, degree or 2 is too much. Crosstalk actually 10 to the minus 3 is too much. That was the most interesting result. But however, you can improve that if you do not use measurements at too far of a distance. So I recommend trying to look at this paper. Tin Deng's, my postdoc, just published. This part just shows for various cases how much the upper plate of the X-ray machine was tilted. It's definitely not parallel when you compress the breast. It's up to 5 degrees. So the point here being, you need to be, for tomography, you need to be very good control of your geometry. So if you can have a rigid probe, that's much better than having a 2-piece probe like we're doing it, but in any case. And the contrast from the tumor is only 1 or 2% of the signal. So that being said, we can switch gears a little bit and talk about something that is slightly simpler in some ways and quite actually sophisticated in some others, which is to measure, essentially neuromonitoring is monitoring brain health. I'm focusing primarily on blood flow measurements, which is fluorescence spectroscopy, though near-infrared spectroscopy plays a role too. I mean, maybe some of you have heard about this, yes, but essentially it's in the spectrum of speckle-based techniques. So essentially it comes from, starts with dynamic laser scattering, where you have a single scattering event and the fluctuations tell you about how the particles move to, there's laser Doppler, which is probably still only one scattering event, and there is diffusing wave spectroscopy, or you have multiple scattering events, laser speckle, depending on how big, if you have a big vessels or not, you will have also a few scattering events, and then DCS is on the tissue level, like the same kind of separations as near several centimeters and many, many scattering events. In the end, scattering from a dynamic scatter is going to cause a phase fluctuation that is going to make the interference pattern of coherent line fluctuate. The faster the fluctuations, the more movement there is essentially. So this is the simplest model is the diffusion correlation equation, which is very much like the diffusion approximation, except instead of having just, the attenuation being the square root of 3 mu s prime UA, it's the entire term. So this is like kind of a dynamic absorption component that has to do with the amount of motion of particles. That's how you measure blood flow with DCS. And what we measure is autocorrelation function. So this is time on a logarithmic scale, this is correlation. This is kind of a bit hard to see, but this is an order of magnitude every time. So this is 1 microsecond here. So essentially this says, no matter how fast things are moving, over 1 microsecond, light is steady. When it says 0 at 1 millisecond, that means over a millisecond, you have no idea what's going to happen with the light. It's going to be random. So in between, the correlation decays. And by fitting this curve, you get the actual blood flow. You have to make a lot of assumptions in the model to come up with a simplified equation like this. But actually, there's been numerous validation studies. It definitely works to some extent. So I'm going to start with the motivation of actually this the project I'm starting now to look at patients that have surgery under Cardio-Pulmonary Bypass. And the bypass machine is amazing, but has potential trouble. It's used for any surgery where the heart has to be stopped. So for example, a coronary artery bypass graft. And sometimes there is a bit of cooling of the patient to protect the brain from itself, because the cooler it is, the less oxygen it needs. That's the major concern, not enough blood to the brain. And perfusion is maintained kind of indirectly. I mean, the blood machine is pumping blood through the systemic circulation. The body is still controlling how much gets to the brain. And when you're under anesthesia and you're sick, that may not work so well. So they do their best, but there's no there are some commercial oximeters that most doctors have met decided they're not trusting them. I mean, they basically rushed out with CW technology, and it kind of works. But from what I know, I expect them to be, only partly reliable. And part of this project is not just the clinical study, but a lot of work is going to go into validating and understanding better how to take the measurements. So the problem with bypass is that there's neurocognitive defects. I think depending on which study you read, anywhere from 20 to 50% of the patients will have some cognitive deficit after surgery. It usually goes away, but even if it does go away, they're going to stay in the hospital longer. It's going to be more unpleasant for them, it's going to cost more, so the more you can reduce that, the better. And there's probably two main mechanisms that might cause this. They all probably have to do with hypoxia, but one is just not enough circulation, the other is microemboli, because when you change the perfusion, just stuff on the vessel walls might get scraped off and go block a small vessel. So optics can definitely deal with the perfusion, and things like transcranial Doppler can actually notice the particles. So by combining NIRS and DCS, we can look at hypoxia, we can look at blood flow, we can look at the rate of cerebral metabolic rate of oxygen, and besides just hypoxia, which is very important, we can also see hypoperfusion. It's probably going to be an early warning for, the saturation is going to come later. Hyperperfusion is not good either, because you could somehow set up the body, make the body have too much blood flow, and it's called luxury perfusion, but also has a bigger chance of scraping something off the wall and blocking a small vessel. With the cerebral metabolic rate of oxygen, you don't want to see that going down, because that, if any starve of oxygen, is going to die very quickly. But the cooling, is trying to take care of that. So anyway, unexpected reduction is really bad. It's probably not going to happen too often. Unexpected increase may not be good either, because they have to cool down the patient a bit in the beginning, and towards the end of the surgery, they actually increase the temperature. And there's there are Arrhenius, equations from chemistry tells you the rate of a reaction actually doubles every 10 degrees, so it's quite a change in the metabolic rate. And you can sense it optically and say, oh, wait a minute, the internal temperatures go too high, because they don't have a very good way to measure internal temperature in the brain. They try to put the probe through the nose, and if it's not open brain, they don't quite get to the actual brain tissue. So there's a lot of information that can come from optics, besides just basic hypoxia and reduced blood flow. So, instrumentation essentially is kind of standardized for many years now. You have some kind of spectrometer, some kind of DCS device. We had a SBR grant to the ISS, and by you I mean Dr. Franceschini, and I was part of the project to just put everything in one box. This is a diagram of the system. It's really pretty much a frequency domain system and the DCS system in one box. Just convenient. It looks like this. You can plug in just 4 PM detectors and 8 wavelengths, and then 8 photon counting APDs for DCS, and 1 long coherence laser. And huge amount of work goes into building these kind of probes that are, every location is a prism, so they're kind of flat, and you can shoot light in. This combines the DCS and NIRS light, and then detectors also combine fibers. And we use multiple distances, and I'll explain later why that's important. And you have a forest of fiber. Usually we put in extras because they're going to break, so we want to have some left after some have broken already. Distance is typical, 5 to 20 centimeters. I think DCS to get 3 centimeter measurement is quite challenging. For frequency domain, probably 2, but DCS is more sensitive to brain. And the interface gives some kind of real-time analysis of the signal, though we post-process everything. So we did a validation study for this instrument. I think titration is expected to work. I'm not even going to go into detail. This has been done so many times. But what we liked was that there's not too much crosstalk in blood flow, because the blood flow value is essentially blood flow times scattering is what you're fitting. You're not fitting blood flow. So if you don't get scattering right, you're going to have blood flow completely wrong. So when we change absorption a lot, or even scattering a lot, the blood flow didn't change that much. When you change scattering, it has some deviation, but not huge. And this was very interesting. We just increased the temperature of the sample. And there's Arrhenius equation. So not Arrhenius. This is Einstein's Brownian motion, and there's models for how this viscosity changes with temperature, because so temperature comes into both here and to viscosity. And we just looked up the parameters and actually managed to get very close to what we predicted. So we use microspheres where you can tell the little plastic spheres, like microns in diameter. You can actually predict what the diffusion coefficient should be, and we came quite close to the real value just by directly measuring everything. So I think the system is fairly accurate. And this is what it looks like when you do the measurement in the clinic. There's a tower of instrumentation here. This is how you attach the probe with this collodion glue that's used for EEG, and it holds pretty well. And then we also put a towel on top so you not have too much light, and measure for hours, like literally anywhere from 1 to 6 hours. And I just have some data to show you this. A lot happens, so we're going to spend a lot of time with doctors to digest everything we're seeing, but the saturation, this is total hemoglobin, this is blood flow, this is metabolism, this is when the person went on bypass, then cooling, and this is when they were being rewormed. At some point they had to stop it to do something, so there's an interesting thing here. There's hemodilution. We're going to always see that. Whenever you start the bypass, they actually dilute the blood so it flows more easily, and you can see total hemoglobin concentration is dropping. Blood flow is actually, in this case, fairly steady. There was some increase during the reworming, which you might expect. Seems like metabolism went up too. I do call this preliminary results because I think it's very challenging to get direct time measurements in adults, and that's, I think, how the final part of the talk is going to be about. This is just using a semi-infinite model and hoping for the best, I guess. But we're definitely not stopping there. So we had some interesting observations, like there was this blood pressure oscillation that pretty much changed everything, which is not what you want to see because autoregulation is supposed to hold the brain steady. But my expectation is that here, the skin is really influencing the signal. And it might be the skin oscillation that you're seeing that's driven by the blood pressure oscillation. The brain may not be varying this much. We have a log from the medical record system of pretty much everything, yes. I can find out. Right. Yeah. Thank you. I mean, there's a deluge of data that comes from that, so definitely we need to start digesting it more. This didn't happen that often. I mean, actually only once was so clear that the oscillation. And then there was another one that was interesting where oscillations developed this time only in the brain. So this is not very easy to see, but the blue is short separation. That's not really closest to the brain. The longer ones in C brain. The blue curve doesn't have that much variation. I actually did a spectrogram, and you can see for 5 millimeter separation there is not much besides the 1 over F noise, but the longer separation definitely had something that appeared at some point and then stopped. So during bypass, this oscillation developed in the brain, and they're not that small. I mean, they look like 20-something% here, and I'll show you later that they're probably bigger than that. So as I was saying, we really want to understand what we're seeing there, because yeah. Good question. Yeah, somebody said that this might be burst suppression from the anesthesia. Again, it happened we did like 17 patients, and this happened once. So I see. Yeah. So a lot of my work is actually been on the modeling side too. I think I have to speed up a little bit, but essentially, we want to understand what we're measuring because, for like a nearest measurement, a 3 centimeter separation, the sensitivity to brain is probably 2% on average. Most of the signal is not driven by the cortex. So therefore, DCS is kind of non-linear, that the more motion there is, the more sensitivity you are to it, but it's still not going to be that much better. So I definitely think there's patients where we do not see the brain, some we do, and I think as a field we need to be accurate. We have to develop a method to tell whether we're seeing the brain or not without the help from CT or MR. And at least I think that's one issue with the commercial oximeters, that they're probably really bent on reporting a value for, if it's accurate or not. Probably if they were a bit more honest, and when this signal doesn't make sense, maybe the doctors would use them more. So in any case, to rush a little bit through this, we had a segmented MRI scan. We simulated the measurements with Monte Carlo code that takes track of the scattering angle of the light. So this so-called momentum transfer can then be converted into the amount of decorrelation, and try various changes in extracerebral and cerebral blood flow. And for inversion, we discarded the knowledge about the internal structure, took only the exterior, because these days you can buy these 3D scanners that you just flip around and get a shape. So we figured that's fair enough to know, even if you don't have CT or MRI. and then shaved through image processing layers to be able to create a layer structure. And this is tunable as you need it. Somebody told me to start, and they said, oh, you have an onion. So that's basically the metaphor. So here is just an example of what happens is if you triple perfusion in the skin, measurements at every separation change quite a bit. If you triple diffusion in the brain, at 3 centimeters you see this differential change, 9 millimeters, you don't see that much. And what happens is that these photons are the ones that decorrelate first, are the ones that travel the farthest. That's why the sensitivity to brain flow is in the beginning of the curve. So then it's become standard practice, I think, to fit only the first part of the curve to get more depth sensitivity. And to make a long story short, if you use the actual geometry, this homogeneous model essentially is going to report the skin. So if its skin is changing, you don't know what's happening to the brain. If there's huge change in the skin, you don't know what's happening in the brain. The problem is they usually tend to go together. So what you're seeing makes sense. It's hard to tell if it was the brain or the skin. That's my opinion. And I think there's people in the field who feel more strongly that they see the brain. And here, because it's simulation, if we do use the actual geometry, even in the layered sense, so without actually specific geometry, just finding a layer thickness where the residual is minimized, we can have pretty good recovery of what happens in the brain. So that just says the layer model helps, but so I don't have time here to go through it, but absorption is like a certain change in absorption will be probably an error about 1/4 of that in blood flow. Scattering is closer to 70%, so yes, they definitely matter. And it's important to know them. And also you need to know how to tune the model. So this idea came from UPenn that you push down on the probe and you don't expect to see the brain change if your model is tuned right. I mean, that's essentially the core of it. So we thought it's really neat and we should try to use it, but also want to understand it better. So I did a simulation and tried 2 different inversions. One is using slabs, because this you can do analytically. You don't have to use Monte Carlo, and that's an advantage because it's analytic. It's numerical. It's still a numerical integration, but it's much faster. Though I have to say, with the GPU processing in Monte Carlo, I can probably do almost real-time fitting anyway, even based on Monte Carlo library. I want to see, using a slab geometry versus the actual more curved geometry, can we simulate a pressure maneuver? So this is simulation. This is input. This is the blood flow I assumed in the brain, in the skin, usually 3 to 6 times higher. And the pressure reduces the blood flow. And then, as I change the assumed superficial thickness, this is what we recover. Now, red is our guess of brain and our guess of skin, so superficial versus deep. And as I change it, what our goal is for this not to change. So at some point, we'll find the value where this is quantized, so somewhere in between it will be straight. And then this is for the slab model. For the curved geometry, it takes a bit longer. I mean, it's a different thickness. And if you plot these ratios, I would say just focus on this. This shows the ratio between the blood flow at baseline divided by the one during the compression, during the pressure. And what you see is you want it to cross 1, because that's where there's no influence from the pushing down on the probe. So either using slab or curved geometry, there's some point where you can basically remove the superficial influence, but this value of thickness is more realistic compared to the MRI, and also the actual blood flow value is still, it was 5 that we put in, we're recovering 2 point something, but it's still twice better than the slab. So there is some value using the curved geometry, and we're still investigating if there's other benefits. I think also the fitting is more stable, so there's actually less noise when you do the 2-layer fit, because it's going to add noise compared to the semi-infinite. But it seems to be worse for slab because there's more model mismatch, so there's more chance of running in the wrong spot because of noise. And we tried this for one of these cardiac cases, and this traces show the pressure modulation. So different distances and different changes. The blue is 5 millimeters, then 20 and 25, and 25 and 30. The title shows you when we push down, the blue went down 86%, 25 meter went down 70%, 30 went 58%. So basically, we're sure the brain didn't change here, and look how much the measurement of 30 millimeter changed when we push down on the probe. So I think semi-infinite is dangerous. And here is, we could find the thickness where this is equal to 1, and then we could process the data This is the Monte Carlo fit. This is a bit more average. That's why it's cleaner. It's not necessarily the microchip cleaner, but we are still digesting what this means. Well, for one thing, the oscillations are actually bigger when you actually focus on the brain. So where they seem to be 30%, now it seems like the blood flow is actually going up and down 50% in the brain. That's significant. I mean, these are pretty slow. It's every minute. So there's many seconds in that minute where your blood flow is half of what it used to be. And that might influence the patient. This particular one didn't seem to have a notable clinical history, but you know, it's one of the things we're going to watch for. So try to finalize. This is actually, I'm working with Dr. Franceschini on this time domain DCS technique where you can select the photons that arrive at a certain time and only compute the correlation for those. So I'm going to go a bit fast here, but essentially you can select the path length, and the longer the path length, the deeper the photons have went. You can tune for more sensitivity to the brain. And this plot is what I mentioned. So, you know, this is using CW years versus time domain years as at a certain gate time, so like 1 nanosecond. DCS is natively more sensitive to the brain than years just because of this nonlinearity with higher blood flow. And with time domain, you can go even higher. And the beauty of it is you don't have to have large separation. You can keep the fiber closer. So you still get a good number of photons, but you select the ones that went deeper. So in a sense, you're avoiding the 1/R diffusion as you go further out. And because, of course, the SNR is something challenging with time domain. So this is what that kind of system would look like. I mean, you can do this with a time correlation photon counting off the shelf. Essentially, what you need is every time the photon arrives, you need 2 timestamps. One is how long from the laser pulse, and the second is on overall time scale when it arrives. Essentially, you gate the photons based on the arrival time versus the laser pulse, and when you take the macroscopic arrival times of all of those photons, and look at their autocorrelation. That's how time domain DCS works. Now, I mean, the same Zimmerman guy, you know, he also built an FPGA-based correlator to actually a time stamper really to do this, so we don't have to buy a DCS-PC card every time because it's super expensive. And you need a very good gated detector, not gated, sorry, a very low jitter detector. It's challenging to get one with good near sensitivity. So MPD in Milano, they gave us some prototypes that have higher red and near infrared sensitivity. They have some, I unfortunately don't have time to go through all the details, but it's quite fascinating. I mean, the instrument response function is very challenging for time domain DCS. You need the pulse long enough, there's still some coherence in the light, but then you're really smudging your step sensitivity. And then on top of that, the lasers have enough power. This is a picoquant STED. It's 500 milliwatts, so it's nice. But the way it functions internally has a hump in the TPSF in the beginning and then another one. So this early hump is essentially bringing you photons from a different depth. And on top of that, the detector, the charges kind of jiggle in the silicon, and it causes a slow decay of temporal response. There's red enhanced ones that are thicker. Essentially they don't decay fast enough. So the first attempt it was working worse than the CW. Right? What's going on? And I started to understand better and better the technical details of how you need what characteristics the devices have to have. But here is an example. So this is a phantom that has really nice contrast because it's silicon oil on top of intralipid on top of silicon. Yeah, silicon oil on top of intralipid. 30:1 ratio of diffusion. And then this is selecting photons. This is the temporal point spread function that includes everything from the laser and from the detector. So this hump is from the laser and the later decays from the detector. And then these are the autocorrelation curves for different thicknesses of the silicon layer from 0 to 2 centimeters for photons at the peak, and then further down. The further down, the more sensitivity you have, and you really do, your coherence decreases. But in any case, we compare this one-on-one with CW-DCS. And when you're looking at photons that arrive around 1 nanosecond later, Benign has, at least 50% better contrast, even despite all of these shortcomings compared to just using regular DCS. So I think we're getting somewhere. Of course, the cost of this is probably 4 times that of regular DCS. So part of my interest is I'm trying to decide which technology to use for my study that I just showed. And I'm very happy that I can work together with Angela to push this because the rest of it is going to have it figured out and make a decision where to go. But it's anything can help when it comes to trying to measure the other. That's, I guess, the point I'm trying to get. And unfortunately, I think I'm out of time. There's another fascinating thing I'm going to very quickly about, which is if you look at the autocorrelation functions for DCS, the shape of it only works if you're assuming the particles move in a random Brownian motion. Which doesn't make sense because that's not how blood flow works. So the best guess of what's happening that I've come up with is from these video microscopy studies of red blood cells flowing in a channel, there's this phenomenon called shear-induced diffusion. And with that, they don't like literally bump into each other, it's more like they distort the hydrodynamic field around them. And if they're concentrated enough, they essentially influence each other. So if you're sitting on a red blood cell in the bloodstream frame of reference, the red blood cells around you are actually going to diffuse with respect to each other. And this is actually a plot from a paper from 1979 of the apparent diffusion coefficient versus the shear rate. And lo and behold, it's fairly linear. So we are really starting to think that what DCS measures is this actual diffusion motion because of the shear rates in the vessels that the DCS light is coming from. It's not everybody's believing that yet, but there is this Jumbo Tang is a postdoc of David Wallace's that has actually tried the dynamic light scattering OCT study to see if there is any radial differences. I probably can go through all the equations, but essentially you can tell axial versus radial decorrelation. And I'm going to go to the plot. That you actually, with this, you can measure the actual electric field. So this is the magnitude, that's kind of what we measure usually, but then you have the imaginary part as well. So what I'm saying here is the red curve is essentially velocity-like motion, and the blue curve is diffusion-like motion. So near the vessel walls, we definitely have diffusion-like motion. And if you actually compute the ratio, okay, sorry, we come up with a ratio of like 0.2 millimeters squared per second per unit of shear rate, per millimeter per second of translational motion of red blood cell. No, sorry, per shear rate, which is 5 times less than the video microscopy study, but it's within an order of magnitude. So this, I think, says that there is definitely some diffusive motion that can be measured at the microscopic level, and how that plays with translation depends on how many scattering events you have, and how big is your shear radius, what the relative values. Because one, and this is the final thing I'm going to say, the decorrelation depends on the root mean square displacement of the particle, which goes with the first power of time for diffusion and second power of time for translation. So the translation part will decay faster. So it may disappear by the time you get to measure, because the curve is initially horizontal. And if your velocity-based correlation, if you could measure it separately, decays first, what's left is the diffusion-based one. There's conditions where that happens, and it's not always happening. I think there's a nice paper from Andy Dunn, which is another alumnus of BLI. They looked at blood vessels splitting. I mean, looking just at the one vessel feeding two, looking at the conservation of volume, they determined that they have to use the translational formulation for displacement to be able to maintain flow, just the mass balance. In addition to scaling by the vessel diameter, which essentially scales for the number of scattering events. So they're seeing translational. I think DCS seeing diffusion at least most of the time, especially like typical large separations. And it's kind of interesting to see if we could ever measure something in between where we can be sensitive to both regimes. So that being said, thank you very much for listening to all this. And that's an innumerable number of people I have to thank. So this is a long list. Of course, I have to thank David Boas and his wife Malignant for just that they've been great mentors for me along the time, and I think I've been very lucky all the way from the beginning of school to now with excellent mentors, and I'm really sorry that my advisor Basan is not here because he went through 12 paper revisions of my first paper, so I learned how to write. And now when people working for me say, "Why are you so picky?" It's important to know how to communicate effectively. And then I can't thank Bruce enough for just giving me a role model for what a scientist should be like. That being said, and the same for David and Mariangela and everybody else. Some of I guess I forgot to include the paper, the picture, but essentially Bin, which is what is here. She's been working with me for a few years, and she just got promoted to the instructor position. And he used to be my postdoc as Amir. There's a few other people that are not in the picture that have worked with me directly, and then this is the entire team. So, as a last point, those of you who know who David Boas is, he moved to BU last summer. He was the founder of this entire optics group. This is the last picture taken before he left. There were 31 of us. He left with 8. So some people don't realize that actually a lot of people are still doing optics at Martinos. There's actually 5 PIs, that are assistant professor or higher at this time. So we're still going. We have a website called optics.martinos.org, and this is the entire group. So thank you very much. And I don't know if there's any time for questions.